1 second right there. So that's just another example of the ones that where I'm going to ask you to draw something you should be able to understand. Not just, the time that we give you isn't always the period, the frequency. Here it was just the time to go from here to here. I know you did something like that in the homework where we asked you how far did it travel from here to here, or how long did it take to go between those different points on a graph like that. You should be able to draw those or read and interpret the graphs of simple harmonic motion like that. Your exam is basically written right now. I think I was counting up points from what we covered last class. There's about 38 points, I think, over what we did last time. And I was telling you there are some very easy points there because there were some definitions in there for period, frequency, wavelength, amplitude. There were definitions and examples for the different types of waves, longitudinal, transverse. And if you found that first homework easy, or that first day of lecture fairly easy, then that's a lot of good points that you can get right there. This is a test that, as long as you're studying and doing the work, it's usually much easier to get an A or a B on this test than it would have been on other ones. There's much less math. I think there's much less room for error than there were on other problems where you could, on a 15-point problem, if you get something wrong or you use the wrong physics, you might be down to a few points out of 15 if you didn't do a free body diagram or something for one of the torque problems. Whereas on these, I think it's much easier to identify what you're supposed to be doing, and it's pretty clear. And we're going to talk about standing waves today, and you're going to have really 3 different types: waves on strings, or standing waves inside of a tube. And it'll be very clear that you have a tube or that you have a string that's going to be vibrating. So it's not going to be a simple exam, but if you're prepared, I think you'll probably find that it's one of the easier ones. That homework, I think a lot of you went through fairly quickly. Really was a lot about just definition and understanding this kind of motion and what these graphs represent. And as I said, there's, as of right now, about 38 points there on that first day's worth of material. We finished up last time with the standing waves. I showed you the standing wave on the string video. We showed a little bit with that spring or the slinky here. Let me just remind you or tell you that on Friday, I'm not going to be here for office hours. I'm sorry, James. I will make it up to you on Monday from 10:30 to 12:30-ish. I'll be probably in lab. I'm going to be doing makeup labs, so you can come to office hours. Or my office. I might, it just depends on where everybody's at, if I have people doing makeup labs or not. But I have a makeup lab scheduled at that time. And actually, if you have a lab that you want to make up for this class, I'll be in lab that day. If you wanted to do it on Monday instead of Tuesday, maybe you're leaving town or maybe you just want to get it done before the test or whatever you want, I'll be in there roughly at this time on Monday, so you can come by then. I apologize for not being here Friday, but there is an assistant coach vacancy job in LA. So I need to go take care of my priorities. But I'll be here Monday. If I'm not there, I'm just coming from a class, so I'll be around. I have a class that ends at 10:30, but if it's late or something, I'll be around at that time. Find me either in the lab or in office hours. And
will you be here from 3 to 5 in office too, or just?
Yes.
Okay.
This is just extra office hours, so that James doesn't cry.
I'm not seeing me on Friday. I didn't see you last Friday.
Why weren't you here last Friday?
I went to the compass test.
Okay.
I didn't take the day off.
Okay.
So if we do need to make up a lab, do we need to tell you which one we need to make up?
They'll all be set up.
Oh, they'll all
Yes.
be set up.
Yeah, we'll have them all set up, and you're gonna do momentum, right?
Number 8.
Yeah, I think. Okay. Do any of you other ones have makeup labs? You need a makeup one?
Yeah.
You do too?
I forget which one it is.
Okay. Yeah, so I really don't think this exam is going to take us much longer than normal class period, but it's usually shorter. But as I told you guys last week, I'll try to give you a little bit extra time on the test, but that means we're kind of pushing into that makeup lab time. So if you can come on Monday, you want to get it done, that'll just give me kind of more freedom to want to go longer with the test if you need it, if I don't have people who need to do a makeup lab. So either way, I think we'll be fine coming up next week. Homework, whatever number it is now, the next one will be up after class. That one has, I think, 9 problems. On my estimated time, this one said probably about an hour. It's not a very long one like the last one. It's going to be longer, I think, than the first one. This one you have some more math on it. I'll put another one up for sound for what we do on Thursday. That one right now only has 6 or 7 problems. Another one that's not as long as some of the ones we've done in the past. There's just not that many different types of problems you can do. I'll probably put up a few more in the course documents area for practice like normal, but there won't be a big long list like we had last time with all those torque problems because there just aren't as many. Okay, so let's just get right into talking about standing waves. So these standing waves are formed by the interference of waves that are moving in opposite directions. We saw this last week. So when we watched that video with the string, where they were oscillating the string up and down, we saw those different wave patterns. I did it with the slinky on the desk, and you might have seen a couple different patterns there. And we saw how I sent a pulse on that slinky, then it reflected back, and it's when those pulses are reflecting and then interfering with each other constructively or destructively at certain points. That's when we're able to create these standing waves. And I think we saw, or if you remember, we saw the different wave patterns that I'll just draw up here. I'm going to put a couple of dotted lines here just to keep them all to be the same width. But we saw patterns that looked like this for these different standing waves. Because remember that video I showed you last week? We could probably kind of see those on that big long rope that they were holding and shaking. Okay. These waves created here by a string or a wire, something with some tension here, are just created by really vibrating one side or oscillating one side, and then we saw how that pulse would go in and reflect off the boundary over here, come back, and those would interfere with each other. And you get these standing wave patterns only at certain frequencies that you're oscillating that string or that rope with. These different patterns are what we call the standing waves here of some string or a wire. The dotted lines I have here are just kind of drawn up here for me to keep them all to be the same width. If you have a string fixed on both ends, I tie it to the wall and I vibrate it here, then the length has to be the same for all of these. When you draw your pictures, sometimes you'll want to draw them, or you'll draw them like this, and there's your first one, and then sometimes people just, they make them longer and longer. And because it's harder and harder for me to squeeze these into the same width here, you can't make them longer and longer like this. This is the same string, and these are the different, what we call harmonics, the different standing wave patterns for that string or that wire. So don't make them progressively longer or wider and wider as you go on. You're squeezing these down here into smaller and smaller of these little loops while you are changing the frequency of oscillation of that rope or wire or whatever it is. So that's what the L is, just the length of the string or the rope. We call this first one here the first harmonic, second harmonic, and so on. These points right here, or these points right here, are called nodes. And the nodes are the points where the string remains stationary at all times. When you are vibrating this string here, these points right here don't move at all. This string here isn't two strings. So I'm drawing it with solid lines here, but this is just the string oscillating up and down like this. And so one of these lines you could imagine as being like a dotted line here. You don't have to draw them that way, but the string can't be in two places at once. It's vibrating up and down like this to create this pattern that you see, but it's only here or here. It can't be both places at once. And so when I'm talking about this right here, these points right here don't move at all. Was there a question somewhere?
Yeah, is there a maximum number of harmonics you can get? Like, is 3 the most you can get?
No, you can keep going. I'm just not drawing more. And I won't ask you to draw it for 50 because that'd be hard to draw. But you can actually go really high. It's not always very easy to see. We saw that with that big long rope on that video that I showed you guys. And those are big loops that you could see. And they're very easy to see. And we could do that. We might do that. I might have you guys try it in lab today if you want to see it with the slinky or even with a rope. You guys could try it to create some of these patterns. You'll see nice big loops like we saw on a string on just the size like this, or maybe even from here to here. You can tie like a string or a rope attached to a wall and then adjust like a speaker to it that's vibrating. Something that you can tune the frequency on it, and you can adjust the frequency so that you get all these patterns. When you're at a certain frequency, you'll get this pattern. And then when you're at the next one, which is actually twice the first one, or 3 times the first one, you'll get these patterns only for given frequencies. Anything in between, you're going to have a string tied to 2 ends like this, and you'll see it and you'll hear it vibrating, but it's not going to make that pattern. That's only when all the reflections interfere with each other to give you this kind of interference here. When they become much higher, they're maybe harder to see, but if you can turn up the amplitude of it, you can get them to be 6, 7, 8, 9, 10. I mean, it's pretty easy to do with a string and a source that you can tune the frequency on. Your hand, you can adjust the frequency and go faster and faster, but you can't get that high with your hand. But you can actually, I've hooked up just like a speaker to it with an adjustable frequency, and it's going to vibrate. And I've done it at labs at different schools where you can see them nice and clear. Theoretically, they can go on pretty high. But the thing on these is that the more you do that, the more you may be affecting the tension on the string. And so you just may have limits there with how many you can see. But theoretically, the number of harmonics can go up very high. You can count up to, theoretically, to infinity. You just won't be able to see them, and you can't create them that high.
And that could actually snap the string.
Probably would. Or your device, that practically to be able to use it and tune that frequency that high, you probably wouldn't be able to get it to go that high. You'd blow your speaker before you, in that case, in the example where I was using a speaker. But I'm not going to ask you to draw any more than the 3rd or 4th one, just because they're a pain to draw. I will expect you to be able to draw these pictures, though, and draw them like this. You can see my loop here isn't the exact same thing as that loop there. It's a little bit different. They don't need to be perfect, but they need to be pretty symmetric. They need to be like this here. It needs to be divided up evenly into nice 3 parts there. And remember, I was saying up here, I've drawn that one as a dotted line. You can do them all that way if it helps make sense to you. But when you're drawing them, it just might be easier to make the pattern like that and then leave it that way with solid lines. They don't have to be drawn that way with dotted lines. But this is just one string, and it's vibrating up and down. And so it's not just 2 strings here with a little loop like that. That's just what it looks like when it's vibrating. Okay. So these points here are called the nodes. The points of maximum displacement are called antinodes. Maximum displacement which is the same thing as talking about the amplitude, right? Maximum amplitude are points like right here and right here. These are what we call antinodes. I'm not going to ask you to define those word for word or anything like that on the exam, but we will be using this language, so you need to know what I mean when I say maybe find the distance between a node and an adjacent antinode. Then you need to know where those points are, you need to be able to mark them if I give you any information about nodes or antinodes. Okay. So definitely know where they're at. We can also say that the distance between adjacent nodes or adjacent antinodes is related to the wavelength somehow. Okay, so let's look up the graph and we'll figure out how much it is. When I say the distance between adjacent nodes or adjacent antinodes, these 2 points right here would be 2 adjacent antinodes. Right? Here's an antinode, here's the next antinode. This point and this point here would be adjacent nodes, or here to here or here. Any 2 adjacent nodes or antinodes here would be separated by how much in terms of a wavelength. So how much of a wave is this right here in terms of a wavelength? Is that a full wave? It's only part of a wave. How much is that? That's half. How much is this whole pattern here?
That's a full one.
Okay. So the distance between 2 nodes, here and here, or here and here, or here to here, is how much? How much is that right there?
Half a wave.
So what's the distance between 2 adjacent antinodes, here to here?
A wavelength.
That's also half, because that's a quarter, another quarter, right? Or from here to here. These distances on there would be separated here by lambda over 2. I'm going to call this lambda 3, just so that you have it written correctly there on your diagram. The lambda 3 is going to correspond to the wavelength for the third harmonic. That's what that 3 notation is going to mean. I'm going to define that in terms of some equations and subscripts for those different harmonics in a minute. But I could show up here that this distance between adjacent antinodes here is the wavelength over 2. So in general, it's just half a wavelength. Okay.
Is that always true?
Yes. This is just half wavelength. The wavelength is obviously different in this pattern here, this pattern here, this pattern here. Does it get longer or shorter as I'm going down here from the first down to the third harmonic? Shorter. Shorter. So each pattern is going to have a different wavelength. But in any standing wave, if it's this standing wave or this one or the 15th one, any 2 adjacent antinodes or adjacent nodes will always be separated by half a wavelength. These little loops here are always half wavelengths. Okay. So the distance between the ends of that would be lambda over 2, where that lambda, that wavelength is just depending on the properties of the string and the tension.
Why wouldn't that last one be lambda over 3?
Which one?
The last one?
This one here?
Yeah.
Because this distance here is still a half a wavelength. This little piece here from here to here is still half a wavelength. This is a full wave. If you're thinking 3, we might be thinking 3 of these loops, but this is 3 halves here. There's a half, 2 halves, 3 half a wavelength, but any separation between these 2 points, these little loops are always half of a full wave. Okay. Now, there is going to be something divided by 3 there. If I'm talking about dividing up this whole length into half wavelengths, then I'm going to say there's 3 of them there, and that's going to be where the 3 that you're kind of thinking of would come in. But whichever standing wave pattern you are in, the first, second, third, or 100th, these points are always separated by that half wavelength. What would be the distance between a node and an adjacent antinode?
The amplitude.
In terms
Be a
of
wave-
Four.
a quarter of a wavelength. So from a node to an adjacent antinode here, then this distance from here to here would be lambda over 4. This part right here, this is from a node to an adjacent antinode. Those are always separated by a quarter wavelength. Because we're going from here to here. And this little part right here, this whole thing was a half, this is half of a half, so that's just a quarter of a wavelength. See that, James? Okay. When you draw your pictures for these, if I ask you to draw the first 3 or 4 standing waves for a wave on a string here, you don't need to show me all these marks that I have on here. I mean, the nice clean pictures that we had with just the waves, that's all you need to label on here in general. I was just adding some more just for your notes. You're gonna get some practice, or you're gonna be doing it on a few problems where I'm gonna have you draw these again. So it's fine to leave all that in there on your notes, but just, if I'm asking you for the standing wave patterns, unless I ask you to label nodes and antinodes and all these things, all that extra stuff there was just me making notes on here, but the wave patterns are just those that you see right there. Okay. We call these the different harmonics. Okay. And we can write the length of that string can be written in terms of the wavelength of the standing wave. Okay. So the L here is just representing the length here, the width that I have here between these walls that I have, the 2 fixed points on the end, the length of the string. Okay. This L, or this distance here, is just the distance between all these little waves that we have in here. Okay. We already talked about this. This is a half wavelength. So what would the length of the string be there in terms of half wavelengths, or in terms of a wavelength?
Yeah.
L would be equal to what in terms of the wavelength here?
L over 2.
Well, lambda over 2, right? Because the length here is just the wavelength over 2. That's a half a wavelength. How many half wavelengths do we have here?
2,
How many do we have here?
3.
So we're just fitting in here between these fixed ends some number of half wavelengths. I have 1 half wavelength here, I have 2 half wavelengths here, I have 3 there. So if I knew what that wavelength was, you could tell me the length of the string, or we could write it like this. This is going to be n times lambda n over 2, where n is just an integer, a counting index for us to tell me what number we are, which harmonic we have there for those standing waves. This n right here, make sure it's clear in your notes. This is a subscript. This n refers to the n that's right here. So this would be lambda 1, this would be lambda 2, this would be lambda 3. Okay. It's the wavelength of the second harmonic, or the third harmonic, or the nth harmonic, whichever n you have down there. That's a subscript here. This is an actual multiplier. This is a number you put in 3 or 2 or 5, whatever harmonic you're on, into this spot right here. Because your length is, like we said, if I have just the first pattern there, the first harmonic, I put a 1 right here, and then my length can be expressed as just lambda over 2. If I put a 2 in here, then my length ends up just being 1 full wavelength. It ends up being lambda 2, because this here is just a full wavelength. That's what we're writing here with this equation for the length of the string.
So no matter how many harmonics we have within a given length, it will always be over 2.
Yes.
That's a constant.
Because we're adding up, we can only create these patterns by making these half wavelengths, and I can go from 2 to 3 to 4, but we're not going anywhere in between. Okay. Anything in between, we won't actually get a standing wave pattern. And so yeah, we're always adding up, fitting in some number of these half wavelength little pieces, from 1 to 2 up to however high we go. And that's what this says right here. that we're just adding up half wavelengths, some number times a half a wavelength, where that wavelength is going to be different for all these different patterns. So you have to keep the subscript here on that n and keep it written. Whenever you write down lambda, it has to be lambda n, whatever that is. Put the number in there and keep it. But you don't use that number anywhere in your math. It's just there as your notation to say which harmonic you're on. Okay. Any questions about that?
So n refers to the number of harmonics, and is that
Yes.
correct?
So here, this is n's equal to 1, n's equal to 2, n's equal to 3. It tells you the harmonic that you want, the number that you want.
Okay.
Okay?
So you would set that up as 2, parentheses, lambda subscript 2 over 2.
So if I wanted to do that over here to show it for this, if I was going to use the equation, the L here would be 2 times lambda 2 over 2, which just ends up giving you lambda 2, which makes sense because the length here is just one full wavelength. Yeah. If I was going to do it for 3, I'd have 3 times lambda 3 over 2, because now I have 3 of these half wavelengths in there for that third one. Or the first one, the L can be expressed as 1 times lambda 1 over 2. 1 half wavelength, 2 half wavelengths, or 3 half wavelengths. But the lambdas change, because we see here that it's getting smaller and smaller, or shorter and shorter here as we go down. You guys see how those numbers are working with the n's in here? Okay. Let's also write down the wave speed is equal to wavelength times frequency. We saw that last week. If you remember in that video I showed you where we were oscillating that string or that rope, and the first harmonic we were going at a certain rate, then you had to double that frequency or triple it to get these different patterns. You have to vibrate that string to get these standing wave patterns. Okay? We have a frequency here of oscillations, we have a wavelength. We can write this as lambda n and fn when we're talking about these standing waves here, because we're going to have different frequencies and different wavelengths for all of these different standing waves. Okay? If we do this, and then let's just take this and solve for lambda n, where your lambda is v, and I put ff here, but you all noticed that, right?
Yes.
Allison, did you see that?
No, I can't.
Yeah, you probably can't see this out loud. I'm just joking. But that's an n here, so this is over fn is equal to my lambda n. Okay. And I just put on the n's here since we're talking about these standing waves now to write an expression that I can use up here that will give us the frequency of oscillations for these waves. Okay. So let's take this lambda and let's put that in here, or let's take this lambda and put it in here. Let's just replace the lambda in one of the equations. I'll go ahead and take this wavelength and put it up into this one right here. So we're going to have n times this lambda is v over the frequency. So this is 2 times fn there. If I replace the wavelength with v over the frequency. And my 2 is still down there from the spot right here. You guys see what I did there? Took this lambda, plugged it in right there. And let's just go ahead and solve this for the frequency. This would give me n times v over 2l. And I'll just write it in parentheses like that to keep the n separate the same way that I did up there. For all of these, I'm not going to write it down every single time we list these today, but these are all for the same n's being all positive integers like that for the n. Okay. So this just gives me an equation for the frequency of the wave in any of these different harmonics that we have over here. Okay. You don't have to show me this step right here to go from this equation to this one down here. I think as long as you know this right here, you can get from here to down here. Most of you will probably just end up memorizing these 2 equations here, and I think you already know this one here, so you won't actually have to show this step. But if you ever get mixed up and you forget, this, you should be able to, if you really understand this, you will know this equation because you will look at these pictures and say, okay, I can look here, I know I'm adding up half wavelengths. this will be something that you memorize. But if you understand it, you can get this from looking at your diagram and remembering kind of how we developed this statement right here to express the length in terms of some multiple of half wavelengths. And you can get down here as long as you know this also. But I think, as I said, you'll probably just choose to memorize the equations. Whenever you're dealing with these standing waves, this is one equation that you'll write down. You'll write down this one for your frequencies and know your diagrams. And you have a standing wave on a string. You'll approach this by kind of just looking at, okay, I know these diagrams, I have these equations. You'll just use them all for your standing waves. It's kind of like when you were doing kinematics, you had 4 equations, you were just picking which one to use. It's going to be a similar thing here where you have these different standing waves on a string or in different types of tubes, where for each different standing wave pattern we're going to have a different set of equations and diagrams for each one. Okay? And so you want to make sure you know all those next week. Okay. Let's go a little bit further with this. We can write this equation one more way. These frequencies, so the frequency for 1 or 2 or 3 would produce these different standing waves. Okay, so this would have a frequency 1 that would produce this standing wave. F2 would give you this pattern right here. This was that frequency that I was talking about. The one that I was saying if I tune this from my speaker or something that I could attach to the string and make it vibrate. Or that was just us kind of oscillating up and down as we were shaking the string, or as I showed you in that video. That's what these frequencies represent, the frequency of oscillation of that standing wave. Okay. The first one, we also call the fundamental. You will hear that word a lot for the fundamental frequency. And you'd have an F1 here, an F2 here, and an F3 here. I'm going to list them here just so that you see it, but that you'd have F1, F2, and F3. These are the frequencies that produce the first, second, or third harmonic. This F1 we call the fundamental frequency. The fundamental frequency is always the first one, the one that corresponds to n is equal to 1. So the length is the same for all the standing waves, but the frequencies are all different, the wavelengths are all different, and those are all indicated by those subscripts for the different harmonics. Okay. So what would F1 be in terms of this equation right here? How would I write F1? F1 would be equal to what?
V over 2L.
Just V over 2L. Right? You just plug in 1 for this one. F2 would be equal to what? 2 times V over 2L. What would F3 be?
I feel like you're trying to ask us a trick question.
No tricks here. What's F3?
3 here.
3 times V over 2L. We're just taking these frequencies in, and everything is one of these V over 2Ls, or 2 or 3. We can then write this equation another way and say that Fn is equal to n times V over 2L, which we already saw. But V over 2L is also which frequency over there?
F1.
The fundamental. All of your frequencies are just multiples of the first. And that's why I have you write it out, or that's why I wrote it out this way, so you can kind of see this is just one of these, 2 of the V over 2L, or 3. This V over 2L is F1 though. This is just 2F1 or 3F1 over here. That's what this says right here. If you know the first, if you know the fundamental frequency, all the other ones are easy to get. If my fundamental frequency was 10 Hertz, then what's the third one? 30. I'm not trying to trick you to death. What's the 10th one if my fundamental is 10 Hertz? 100. They're all just multiples of the first. So when you know the first one, all the other ones are very easy to get. Right? It's just a multiple of f1. Okay? This is another very useful equation if you happen to know the first one. If you don't, then you might use this one. Okay? Sometimes people write these down, they're not really sure when do I use this form or when do I use this form here. It really depends on what you know. All right? If I've given you the first, of course you're going to want to use this one right here. Or if you can find the first, then you shouldn't have to go through and recalculate this every single time because it's going to be the same. The v is not going to change for the speed of the wave on that string, and the length isn't going to change because we're not stretching it at all for any of these different patterns that we have here. One more equation that I'll write down is for the speed the wave. We can say v is equal to the square root of ft over mu. Okay. I'll tell you what these mean here right now. The ft is just the tension we're using an ft instead of a t. Why do you think I've switched this now in this unit? What else do we use a big T for?
Or period.
Period. So you don't want to call this T for period because we're definitely going to have wavelengths and frequencies in here. That's why we're using an FT now, but this is still just some tension force. You aren't going to have to calculate this tension force from a free body diagram like we were doing before. This will be something that I ask you to solve for, maybe from the equation here, or maybe a force that I give you. But there isn't going to be a big complicated free body diagram to solve for that force. Okay. The mu is the linear mass density of that string or wire or rope, whatever we have there. And this is just mass per length. With units of, well, mass per length. So what's the unit of mass?
Kilograms.
Kilogram. And the unit of length?
Meters.
So don't confuse these m's here. This is a kilogram per meter. This is a mass per length of the string. And let me just go ahead and write this out so that you have it there in your notes. You can put the little m there if you want to, but I don't want you to confuse this with the unit for the meter. And L is the same L we've been dealing with up here, the length of that string. So this is one more equation that you have for your standing waves on a string like this, okay? So if you're dealing with a standing wave problem on a string or a rope or a wire or something with tension like this, then you have this set of equations here. This one, this one, this one, and the one over here in red. This was an intermediate step that we used to derive that right there, so you probably don't need to use this all the time. But you have all these equations that you use to analyze these standing waves over here. So the minute you know you're working with a standing wave in a string, you should be thinking about all these equations right here, or maybe write them down, draw your pictures if you need them. And then it's just a matter of using them to solve for something. The frequency, the wavelength, the tension, anything in here. Okay. We're going to have diagrams like this and sets of equations like this for 3 different cases. A string, a tube that's open on both ends, or a tube that's open only on one end. Okay. These standing wave patterns are created on strings here. So on a piano wire, on a guitar string, when you create these nice clean harmonics is when you're producing the sound at a certain note at a certain frequency. Okay. Inside of a tube, a column of air, like a wind instrument, a flute, a clarinet or something, you're making these standing waves in there either on a string for a wind instrument or in a column of air later on. That's what we're looking at. We won't talk a whole lot about music in this class or how we use these things or what we're going to be doing with the standing waves. We're really just looking at the waves right now, but that's where you would see some of these things in nature, is you're producing these standing waves on strings and instruments. You've seen us do it for fun with the slinky or that rope, but that may not be fun for everybody. Music, for some, is fun. Okay. So, what I'd recommend doing is when you're done with class today, or at some point, make 3 separate pages of notes that summarizes all this together, one for all the different kind of patterns we're gonna get, or for one of those 3 different cases. You should have a sheet or a piece of paper or something where it's all summarized, however you wanna do it, but they're gonna be a little bit different for all of our cases. But once we know which one it is and we have the correct equations, and then we're just gonna apply this to 3 different situations. Yeah.
So the units for the speed of the wave are kilograms per meter, or?
No,
is
the
that-
units of the mu.
Okay.
This is all just here for the mu right there.
Okay,
And the speed of the wave should be units of,
meters per second?
yeah. And you'll get that when you plug in a newton here and you plug in a kilogram per meter down here.
Got it.
Okay. Let me leave all this up here so that you guys can look at it on the board while we do some problems with it.